Applications of first-order differential equations. The behavior of some real-life systems or phenomena could be described in mathematical terms, or generally, we call them mathematical models. A mathematical model is built based on the assumptions that describe the relationships among the quantities to be studied. It involves dependent and independent variables as well as parameters. For example, mathematical models are used in the study of population growth, radioactive decay, cooling of bodies, mixtures, and the electric current of a series circuit. In this chapter, we are going to solve some mathematical models that are first-order linear differential equations. The mathematical models will be solved by using the methods that we have learned in Chapter 2. We will also deal with the inertial value problems and proportionality in order for us to solve the models. It is important that we have a firm understanding in solving the first-order linear differential equations to help you progress in this chapter. At the end of this lesson, you should be able to solve growth and decay problems. The model of population growth is based on the assumption that the rate at which the population of a country grows at a certain time is proportional to the total population of the country at that time. The more people there are at time t, the more people there are going to be in the future. If P of t denotes the total population at time t, then this assumption can be expressed as dp dt proportional to kp, or dp dt equals to kp, where k is a constant of proportionality. Note that this simple model, however, does not take into account many factors that can influence human population, such as immigration, emigration, death, and birth. In general, the inertial value problem is given by dp dt equals to kp, subject to p of 0 equals to p naught, where p naught is the inertial population. Example: a culture initially has p naught number of bacteria. At t equals to 1 hour, the number of bacteria is measured to be 3/2 of p naught. If the rate of growth is proportional to the number of bacteria p of t present at time t, determine the time necessary for the number of bacteria to triple. Solution: we can use the growth model to solve this problem. The differential equation is given by dp dt equals to kp. Since the initial population of bacteria is given as p naught, then the initial condition for this problem is p of 0 equals to p naught. Now, we need to solve the first-order differential equations. By using separation of variables, separate the variables of p and t on each side. Then, integrate both sides with respect to each variable. This will lead to the general solution p of t equals to ce to the power of kt. Next, use the initial condition p of 0 equals to p naught to find the value of c. C equals to p naught. Therefore, the equation of p becomes p of t equals to p naught e to the power of kt. We are also given when t equals to 1 hour, the number of bacteria is 3 over 2 of P naught. Use this information to find the value of K. Therefore, the equation of population at time t is P of t equals to P naught e to the power of 0.4055 t. To determine the time necessary for the number of bacteria to triple, let P of t equals to 3 times P naught. Solve for t, and this will give us the time taken for the number of bacteria to triple, which is equals to 2.71 hours. From the given example, the solution of the problem are determined by an exponential function e to the power of kt. This exponential function increases as t increases for k greater than 0. However, the exponential function decreases as t increases for k less than 0. Thus, the value of k will determine whether the problem is related to a growth or decay problem. Therefore, the positive value of k will yield to a growth model, whereas the negative value of k will yield a decay model. Quick check exercises. Write your answer in the comment section.